something today before class, Jonathan, and you had a question about problems. I'm going to do problems today, all right? So any questions you have about the problems, I'll address. He was the first that came to me, so he'll get it. This is a capacitor problem. What problem is it?
It's 3.32.
32. So here's basically what I remember. You had a voltage here that was, I think, about 12 volts. And then you had, correct me if I'm wrong, right? And then you had a resistor here, and then you had a capacitor here. Ooh, better be careful. Yeah, I think you had a capacitor here. I'll put the switch in a second. And then you had another resistor here. Am I right so far? And what else? A switch here?
Yeah, the switch coming down.
And then a resistor here, right?
Yeah.
And this was 2K, is that right?
Yeah, it was 2K and then 4K, and then the other one was 6K.
6K. And switch closes it to equal 0 or opens?
Closes it to equal 0.
All right. And C was equal to what?
200 microfarads.
200 microfarads. Okay. Everybody follow me on this? I'm going to try this one. I gave the solutions, right? And it's smart to do them when I give them to you, because here's what happens. Then today you're going to get more homework. If you're behind in the last set, you're probably going to be really confused about the next set. Keep up with this stuff, because it starts coming at you faster and faster. Next thing I'm going to do is this. The steps, the order you do this is not important. I always start with the voltage across the capacitor for t less than 0. For t less than 0. So I'll draw the circuit to this one time. What does a capacitor look like for t less than 0? It's an open circuit, right? Nothing's changing. Do you all agree with me? So a capacitor looks like an open circuit if nothing's changing. So if I redraw that circuit, so this is plus or minus 12 volts. There's 2K here. Then there's where the capacitor was, and this is the plus minus voltage on the capacitor right here. That's 4K, and that is 6K, correct? Do you agree with me, everyone? Now follow me on this one. This is a simple circuits problem. If I look here, do you see the 4 and 6 can be combined because they're in series? How many see that? Can you all see it? Now, if these two are combined, somebody asked me to draw this on a, is it all right if I combine them here? Or do I, okay. If I need to, I'll redraw it again, but for this one, I think it's okay just to make this 10K. And now,
just a question, is there any convention to which direction you tend to combine them, or it doesn't matter?
Well, if they're,
I know it doesn't matter, but just, is there a
I like to put them vertical
simpler?
so I can say that I'm showing you this voltage is in parallel with that. That's my next step. So I can put it this way. It's clear this way. Does everybody follow me on this, class? Now, this is important. You all see that this 10K is going to have a voltage, right? And it's going to be identical to that voltage across the capacitor. Does everybody see that? Show of hands here. Make sure you do. I mean, you got to be convinced of this, like in your soul. This can't even be a little bit uncertain. Now, what is that voltage? Do you all see you have 2 resistors in series and a single source, right? We could do voltage division and say that VC here, for t less than or equal to 0, would be equal to the source voltage 12, right? And then it's times the resistance you want the voltage across over the sum of the two, or 12K. And that means it is equal to 10 volts. Can everybody see that? How many can? Show of hands. Make sure you see this. It may seem trivial, but I've got to know it's trivial. Now, after I get that voltage for t less than 0, so now I've got it, it's 10. The next step is find the voltage as t goes to infinity, right? Now, I'd like to erase that board. Everybody got this? Okay? Yes?
Why are they?
Well, here's what I did. for t less than 0, this switch is open, right? We can get rid of that, right?
Right.
And now I want the voltage across this, which is an open circuit, right? You see how the 4 and 6 are in series? If this isn't there?
Yeah.
Okay, that's why.
But why?
Because then wouldn't these two be in parallel with this capacitor right here?
It's parallel with the capacitor.
Yeah, we're always after the voltage across the capacitor, right? That's the thing, voltage across capacitor.
So we're not asking what it is in relation to the other resistor, just the.
Voltage is always in relation to 2 points, right? I want it across the capacitor, so it's always between this point and this point, which happens to be the same thing as this point and this point.
Thank you.
Electrically, yeah, yeah.
So just so I'm clear on this, when t equals 0, the
Less than 0.
Sorry, less
T
than 0.
equals less than 0, yeah.
The capacitor functions as an open circuit
Yep.
because current hasn't just started flowing through it. It's been flowing through it so that it's effectively.
Remember this always. You've had it in physics. If this is plus or minus the voltage across the capacitor, and this is the current through the capacitor, and it's C. I through there is C dV dt, right? The definition. Well, if nothing changes with time, go back to the beginning of anything. I mean, go back 1 billion years. All right? Nothing's happening. The rate of change of time of the voltage is 0. If the voltage change is 0, it means I equals 0, right? If I is equal to 0, it's an open circuit. You can replace it. Yes, sir.
So this is kind of similar to her question. I'm just wondering if it's, you could also solve for the voltage at t less than 0 by just finding the current across that circuit and doing 12 volts minus
You
I
can do
times.
this. Listen, there's a lot of ways. This is the easiest. But if you want to find the current flowing here, right? That would be 12 volts over 12K, right? 1 milliamp, right? Take 1 milliamp times 10K, you got the voltage.
You could also just do subtract I from
Sure, you
2K,
could take
right?
12 minus 2 times 1 milliamp, 2K times 1 milliamp. You get the same answer every which way you do it. So, it doesn't matter to me. Just make sure you know how to get the right answer. Yes?
This is pretty elementary, but can you just say what the formula for voltage division again?
Sure.
You get 10K, which is the opposite resistor, and then over.
Not the opposite, no. Look, if you have 2 resistors in series, R1 and R2, and you have some source voltage here,
I see. You're
the
solving.
voltage across R2 is just equal to the source voltage times R2 over R1 plus R2. That's it. It's always the if you want voltage across something, you take that something and divide by the series net series resistance and multiply it by the voltage across everything. Okay? Straightforward. Getting back to this. So now what's the voltage as t equal to infinity? Well, when t goes to infinity, what's the next thing that happens? Yeah. Did you have a question? Did you? Okay. Well, at t equals infinity, this switch is closed, right? If that's closed, how many see that 6K gets shorted out? You all see that? How many do? When that's closed, this 6K is not even a factor because that's a direct wire across there, right? So now I'm going to redraw that circuit here. So it looks like this. I have 12 volts. Then I have 2K. 2K. Then I have plus the minus V CT goes to infinity. And then I have 4K, and I'm going to do something. I'm going to put the 4K this way. And I ignore that resistor because once that switch is closed, it is not there. Y'all see that? It's shorted out. How many do? It's shorted. You want to know what a short is? Just think of a screwdriver and put it across any 2 contact points. That's a short circuit. Now, what is the voltage across this capacitor? It's the voltage across the 4K. Isn't it, class? Everybody agree with that? So what is it? Well, that voltage would be what? Source voltage would be 12, right? then voltage, the resistance I want the voltage across is 4K over the sum of 4K plus 2K, or 6K. Y'all agree with me? What's that gonna be? Well, 12 divided by 6 is 2, 2 times 4 is 8 volts. So this is 8 volts. Everybody agree with that? Now, what's the next thing? We have to calculate one thing. Anybody? R Thevenin for t after the switch closes, or for t greater than 0. So it's this R Thevenin, right? That's after the switch closes. It looks like that. That's 4K. So what is R Thevenin there? Well, for R Thevenin, what do we do with the sources, class? Turn them off. What does a voltage source become? Short circuit, a wire. It becomes a short. If it was a current source, it would become an open circuit. Short circuit. Please watch this. People mess this up. It concerns me. Now, can you all see that these two are in parallel across these 2 points? How many can? It's very obvious. People will put them in series for some reason. It's like a knee-jerk reaction. They don't think, they react. I don't know why. Your engineers, please don't do that. Think, not react. So between here and here, we have 2K in parallel with 4K. So what is R Thevenin? Well, it's equal to what? You could say 2 times 4 over 2 plus 4, that's 8, 6K, right? Correct, class? This is actually K squared here, and this is K. So you get that. Well, that's what? That's 4/3. 4/3 K ohms. Now, we're not quite done. What else? Let's get the next constant we need. After I get R Thevenin, which this is, there's one other thing that follows suit for an RC problem. What is that? Tau. And tau is R Thevenin times C, right? So it's 4/3 of a K times 2 times 10 to the minus 4th. That's going to be, I think, 0.266, is that right? Just do it for me. 0.266 seconds, I think. Correct me if I'm wrong, is that right? Just take 4/3 K times 2 times 10 to the minus, or 2 times 10 to the minus 4, right? Thank you. Just making sure. Now, I get that, and now what do? I write the general equation, and I apply the boundary conditions, or the values for the voltage across the capacitor t equals 0 and t equals infinity to get the constants. Correct, class? Let me write the equation. You guys will pick up on this very quickly. So now, the general equation is VC of t is equal to some K1 e to the minus t over tau. I'm just going to leave it as tau. I know it's 0.266, right? Plus K2. Right off the bat, please listen. What do we know about K2?
That it's 8 volts.
Voltage at t equal infinity. K2, right? And at 0, this would be a 1, wouldn't it? And you would have a K1 there. As t goes to infinity, doesn't this go away, class? How many see that? So K2 is the voltage as t equal infinity. And that's 8 volts, isn't it? Can you all see this? That's 8 volts. Is that all right? I did that? Yeah? Okay. I want to make sure. If you want me to write in another line, I would. You all follow me on this, class? Now, how do I get K1? At t equals 0, right? What is e to the 0? That's the term. E to the 0 is 1. If you interact with me, it'll stay with you better. Trust me on this one. This is an old military thing. All right, so at 0, this is 10, isn't it? 10 equals blank plus 8. 2. So just make that 2. Now you have the general equation for voltage across the capacitor for t greater than 0. You'll have to put this one stipulation. I'm not harsh on you for that. But this is for t greater than or equal to 0. It starts at 10, decays to 8. Everybody with me? And it stays at 8. You'll notice it stays at 8 for one very good reason. Even with this switch closed, there's still a voltage that's active in the circuit. And that's important. It doesn't decay to 0. Got it, everyone? All right. That's that question. If I asked you, I could ask you one thing. What's the current through the 4K? How would you get it? That's a legitimate question. What? Anyway. Well, do we have the voltage across it for t greater than 0? I got VC, don't I? Just divide that by 4K, I got the current. Are you with me? It's that easy. Now, what about the current through here? How would I get this current? This is a little tougher. How do I get that current? Anyway, let me ask you this. Do we know the voltage across this for t greater than 0? We know this voltage, right? So if I took 12 minus VC, that would be the voltage across there, wouldn't it? 12 minus VC would be the voltage across there, divided by 2K, you've got the current. Follow me in this class? And that's the way you do it. Another question. Are you ready? This is a really dirty question. How do I get the current there? There's several ways. There's a real easy way. First, you have the voltage there, yes or no? For t greater than 0. Yes, right? What is the current through that capacitor? It's the derivative of the voltage with respect to time times c. You see that? You can go right to this guy. If you've got the voltage across the capacitor, you have the current just doing that. Are you with me? How many see that? Don't get nervous. This isn't tricky, but I have to tell you things you need to consider and know how to do. Okay. Now, yes.
Could you show how you got K1 again?
First, we got K2 first.
Right.
Once we got K2, we have 8, right? And that's K1. So K2 came from t equal infinity. The other point was at t equals 0, right? At t equals 0, we had this. At 0 or greater than 0, I mean, at less than 0 or 0, it's 10, isn't it? Right there, do y'all see it? Can you see it up there? Right? It's 10. 10 equals blank plus 8, 2. That's how. That's how. Next question from the audience. Anyone? I figured by now, I threw a ton of problems at you, right? You got inductor problems as well as capacitor. Yes, sir. Which one?
I just had one quick question about that. The current through the 6K is 0 once the switch is engaged.
Oh yeah. Once this thing closes, that current's 0. There's no voltage across it.
And you treat the 4K as being in parallel with the capacitor.
What?
And then you treat the 4K as being in parallel with the
Yeah. Absolutely. For t greater than 0. Now these are simple RC transient circuits and LC transients. In the real world, there's usually RLC, but that's a second order equation, and we don't do them in this class. But if you're interested, you can take a look in the book, and there's solutions I put up there for second order solutions. But for second order equations, the solutions are a little different, and what you do is write the differential equation and then take the Laplace transform. That's the easiest way. When I teach general circuits, that's how I do it. Yes?
Quick question, will we be dealing with capacitors in series or parallel?
You mean the addition of them? That comes, yeah, I'll get to that, yes. Right now, single capacitor, single inductor. Yes, sir?
For that problem, the triple multiplier is to solve for I not 2. How is that?
What, say again?
What is to solve for I not 2?
Through what? What is it through?
It was through the 4K capacitor.
What's that? Yeah, everybody's talking. Through what?
I just wanted us to find the current.
All right, we had the voltage across it, right? Wasn't that VC class?
So we just do the.
Just divided by the resistance, 4K, and you got the current. Y'all agree? All right. Now, another problem. Let's make the best use of time. How about an inductor problem? Anybody? You did the homework. Give me one that you didn't get a little trouble with. Anybody? Yes.
3.19.
Okay. 3.19. I didn't assign that one, did I?
Oh, I just picked it because it looks.
No, this is adding inductors, I'm not there yet. Transient problems that I assigned, please. Just picked it to cause me grief, yeah, all right.
How about 3.35?
3.5? Okay. Now, this is not bad at all. 3.35. Here, you have a current this way, and it's 100 milliamp. Then you have a switch here, and the switch closes at t equals 0. Then you have a resistance of 6K. Then you have an inductor. 0.10 Henries. And then you have resistor of 3 ohms. Oh, that's not 6K, that's 6 ohms, sorry. Okay, for this one, we worry about, with an inductor, what do we worry about always? Forget what they want. What do you worry about? Current through the inductor. You worry about this. That's what we're after. Now, it's the same form as the equations as before, but now we're after the current, not voltage values. So we start by saying, at least this is the way I do it, IL for t less than or equal to 0. Now, what does an inductor look like for t less than or equal to 0? It looks like a straight wire. The reason is, it is a straight wire, just wound up, right? And now there's no time-varying magnetic field, so it is literally just a short circuit. So this looks like a short circuit, right? So for t less than 0, the circuit actually looks like 100 milliamps. And then you have 6 ohms. And then you have just a short circuit, and this is IL here for t less than 0. And I'm going to put it in here, but you're going to see we don't need it. And then you have 3 ohms here. Now, how many understand that this 3 ohms has no bearing on the current through that wire? How many see that? Because that wire shorts all the current through itself. Do you all see that, class? So because of that, I just erase it. It doesn't do anything for me. Now, how much current is flowing there? This doesn't take much sense. How much? All of it, 100 milliamps. I mean, just, there's nothing else that can flow. So this is just 100 milliamps. How many see this? Now, part 2, we need the current as t goes to infinity, right? Correct, class? I'm going to slow down, make sure you see this. All right, so now the switch is going to get thrown, all right? It's going to flip states. When it gets thrown, I'm going to draw right here. This becomes a short, doesn't it? When that's a short, how many see that all the current's just going to circulate here? There's going to be no voltage difference between these 2 points. Give me a show of hands if you see that. So literally what you can do is this. You can just say, all right, I'm doing this for t. This is going to be t greater than 0. Really, it's going to infinity. But since that's the case, to emphasize the point, I can just take that and short it, can't I? How many see that? Right? Literally, because what? That was a short circuit when that shorts, right? Everybody got that? Now, if that's the case, are there any sources in there to sustain that current? None. What's the current going to go to? 0. That's right. So that goes to 0. Now the third thing, I need my R Thevenin, right? Correct, class? Well, how do I get R Thevenin? After the switch changes state, I can erase whatever it is. It's the same if it was a capacitor, right? And I look at the resistance, the Thevenin resistance across these 2 points. I will slow down because I've been asked to. Some people say you erase things and don't have time to computer redraws. Everybody with me on this? That's our Thevenin. How many see that those 2 resistors are parallel? So it's going to be 3 times 6, 18 over 3 plus 6, 9, or 2 ohms. Correct, class? How many see that? It's 2 ohms, so therefore, our Thevenin is 2 ohms. And then what is tau? Now this is an LR, it's what? L over R Thevenin, isn't it, class? You remember that? It's R over L. I mean, L over R. And what is that going to be? L is erased. What was it?
0.1 Henrys.
0.1 over 2, right? So that's 0.05 seconds. Agree, class? Now we put the equation together. We say, I know my I L of t is equal to k1 e to the minus t over tau plus k2, correct? I'm just putting down the general form. Remember, the k's in this have to do with current. Right? Now when you look there, what happens? Well, k2 is what? It's something at infinity, right? It's the value of current at infinity, isn't it? What's the value of current at infinity? I hope I put it there.
0.
Is 0. So K2 luckily goes away. Now, what's K1? At t equals 0, it's 100 milliamps. At t equals 0, this goes to 1. K1 is 100 milliamps. Do y'all see that, class? So that means IL going through that inductor for t greater than 0 is going to be 100 milliamps. Then it's going to be times e to the minus t over tau, which is 0.05 seconds. Or you could say e to the minus 20t if you want. Agreed? What did they want in that problem? That's IL. Did they want something else?
They wanted the current going through the resistor 6 ohms.
Through this one?
Yeah.
Alright, now let me just show you. So I got here flowing this way, really it's going to be right here. So let's see. I have here a current equal to that, which is really 100 milliamp e to the minus t over 0.05. That's the current flowing here. Do you all see that? Now, some of it goes this way, and some of it goes this way. You see those 2 resistors are in parallel? How many see that? If they're in parallel, can't we use current division? I can say the current going this way, I'll call it I6, 6 ohms I mean, I of t sub 6, that is equal to the source current, or 100 milliamps, e to the minus t over 0.05, and then you take that and use current division. So you take the opposite resistor, 3 over the sum of 3 plus 6, or 9, or 1/3 of that. Now that's going this way. You all see that, class? My current that I solved for is going down. Now, if they asked for the current going this way, it would be minus that. Can everybody see that? I'm going to see this right now. Yeah, all right, good. Yes, sir. Go ahead.
Oh, I just wanted to ask how you know that the current's going down.
Well, the convention that I used was I defined current from top to bottom. All right, so that was the convention I used. If it was going the opposite direction, it would be minus that. Remember when I drew the problem, I said the current going in that direction, correct? So I defined the convention at the very beginning of the problem. Through the inductor. Yeah, maybe, man. Go ahead.
Will all the conventions on the test be defined for us?
What?
Will all the dimensions on the test, or directions on the test be defined?
Well, I will give you, when I say I want a current through an element, I'll show an arrow the direction I want the current. and I'll put it next to the elements. Don't worry, you will have there's no ambiguity on that one. Yeah,
The current source doesn't play any part in the.
why doesn't it play any part? Anybody? Short it out. If it's shorted out, it can't do anything. It's a direct short across. Think of this, what happens when you put a direct short across a car battery? Nothing. Your car is dead, it never starts if you short it, right? It's like the same thing here, the thing's shorted out. Other questions about this one? Can I move on to another one? Now somebody got another one for me? That's an inductor problem and not just adding them together. So somebody, anybody? I gave you a lot of problems. I was hoping you did some of them. Because some of them were tricky. There's a couple of tricky ones in there.
You do 3.36.
Is that an inductor problem?
Yeah, it's the one right after the case worked.
But, I mean, I've taught this a lot. I could go into a lot of theory and go to the next chapter, but I know if I don't work these problems, no matter how many solutions you have, you're gonna be uncertain about things. Oh, 36 you said, right? They actually want this current, is what they ask for. And that's a sucker play. Anytime I see an equation for that first, it's like no credit. You don't do anything with that. You always do what? You want to get the current through here, right? So I'll just call that IL of T. For the gentleman that asked about the conventions, this is my personal convention. I go from top to bottom of these things. Right? So I define the current in that direction. Now, after that, it becomes just going through the steps. First thing I find is what, class? This is Baginski's rules, not yours.
IL and
IL for what?
T is less than 0.
Less than or equal to 0, right? Now, what that implies for this one, the switch is closed, isn't it, class? The switch is closed, correct? I mean, it opens to equal 0. Can you all see that, by the way, in the far back? Can you guys see it? Switch opens at T equals 0. Now that means it's closed. When I look at this, I want you to take a look. For T less than or equal to 0, because the inductor looks like a short circuit, doesn't it, class? Right? I can redraw that circuit and I can have this. Then I have 2 ohms. Then I have 6 ohms. And then I have this is where I want the current, IL, right there. And then I have, now can you all see that the 4 and 8 are 12? How many see there are 12 ohms there? I'm going to just replace them with 12 ohms here. I want this current, right? How do I get that current? There's a lot of different ways. I'll show you the way I do it, okay? Are you ready? This is me, not you. You can do it any way you want. But when I take a look at this, what I do is simply say, well, 12 and 6 in parallel is 4. Do you all agree with that? How many see that? So that's 4. Well, 4 and 2 is 6. Can you see it's in series with 2? Give me a show of hands if you can. Y'all with me on this? Can you see it? So I've got 6 total ohms here, understand? And I have 36 volts, don't I? So what does that mean the current here would be right here? That would be I equals 36 over 6 or 6 amps. How many see that? This is the way I'm doing it. I found the parallel combination of the two resistances, 4 ohms, and I added it to the two because they're in series, and that's the total resistance that's across that source. Can everybody see that? That means if I take that total resistance and divide it in with 36 volts, I get the current. It becomes 6 amps, correct? Now, of that 6 amps, how much flow this way? Remember, there's 6 amps going to be flowing here. How much flow this way? How do we do it? People?
Current division.
Current division. Now I take the 6 amps, the current flowing here, IL, would be equal to the 6 amps, and it would be times the opposite resistance over the sum for 18, right? So that's 2/3 times 6, right? Or 4 amps, isn't it? How many see this? Now, you don't have to do it that way. Let me just mention something. What you could do is say, I will do a source transform here. I can get 18 amps in parallel with 2. Follow me? Can you all see that? Source transform. Then I would have 2 in parallel with 12. Would be 24 over 14 ohms, and then I could do current division again. I'm just telling you, there's not just one way. But I'll tell you the way I do it, because to me it's the easiest. I would just take the parallel combination of those two, add it to 2, divide that into 36, then get this current. After I add that current, the amount of that current that goes here would be that current times 12 over the sum of the 2, which is going to be 18, and multiplying by 6. Got me on this one, class? How many see this right? But you can do it any way you want. So that means this is equal to 4 amps. Now, the second thing is IL for t goes to infinity. Again, this is Baginski's method. Well, what happens to the switch for t greater than 0? Yes?
Wait, so for the current division, why is it 12 instead of 6? Because don't you want the 6?
You always take the opposite resistance, right? I'm just going to make this point clear. If I just look at these two, isn't that 4 ohms there, class? Right? I mean, it's the parallel combination is 4 ohms. So the voltage across either of these is 4 times 6, isn't it? So that's 24 volts, right? 24 divided by 6 is what? 4. All right, you can do it that way. I don't care. Do you have a question? Now, what is it at infinity? Well, at t greater than 0, this blows away, right? Do we have any sources in the circuit then, class? No, it's disconnected. There's no path for current to flow through that 36 volts. Effectively, it's out. So I know that IL t goes to infinity is 0 amps. Give me that. Right? Now remember, this is t greater than 0. You all see what I'm doing here? That circuit is open, so that 36 volts has no effect on this. The only way it does is that current can circulate through it. Can you all see that? Now, the next thing I do is I want the resistance, Thevenin equivalent resistance. So I'm going to erase this right here, and I want the resistance between these dangling ends. Correct? Now, please watch this. This part of the circuit has no effect. It's been taken out because it's open. That circuit's open, right? How much resistance is across that? Well, it would be 6 and 4 is 10, right? And 10 and 8, 18 ohms. Do you all see this? How many do? 18 ohms, right? Sure. So, R Thevenin is 18 ohms. And by the way, then what is tau? What was L in this? I'm bad about that. What was it? 2 Henrys? So L would be 2 over 18 or 1/9 of a second, right? Now we put it all together and we see that IL in general of T is K1 e to the minus T over tau plus K2. Are you with me, class? Yes, sir.
Is that 8 ohm resistor supposed to be 12, or I just missed something?
I couldn't get what?
Is that 8 ohm resistor on the right, is that supposed to be 12, or did I just miss it?
Well, 4 and 8 is 12, isn't it?
So you just,
4 plus 8 is 12. You see? Take a look over here. I had 6, right? And then I had 4 and 8 here, so that's 12.
Oh, I got you. You combined the first.
Yeah,
one, so I
I'm-
missed it.
I'm sorry.
I got you.
That's the second person that caused the problem. Are you okay with this, class? Everybody all right with this? All right, now, just look at this. What is K2? Well, it's the current at what? T equal? Infinity. What is the current T equal infinity? 0. I'm not trying, I'm just trying to get you to respond so I know you're there and it'll help you remember, trust me. What's K1 gotta be? 4, yeah. This is just 4 e to the minus t over tau, and which is 1/9 amps. Now that's the current that flows. This is for t greater than 0. This is the current, literally, we know this current. That's the current that flows here. This is IL of t, right? Can you all see that, class? That's the current. We just figured it out. That's flowing, correct, class? Please watch this. Now, y'all see they wanted the current going this way, right? Can you see it's the opposite direction of the current I have? Because all the current has to circulate here. Y'all see that? And that means the I that they want is just minus the I that I solved. Are you with me, everyone? That's all it is. Can we get one with a harder inductive problem? Something where you got a current that isn't going to 0 if t goes to infinity? Anybody going to give me one? Anybody do them? Everybody's looking at me like, don't ask that, you know. From my perspective, you gotta see what it looks like here.
I have a question. When we were finding the Thevenin resistance,
Mhm.
why do we have the gate open?
Because it's for t greater than 0, right?
So when all
Didn't the switch open up at t equals 0? It stayed open forever.
okay,
That's what it means. It doesn't change the state after that.
so we take the Thevenin resistance
After the switch doesn't swing, that's right.
Okay.
You don't care what it looks like before 0.
Okay.
Guys, do you have anybody got a tough problem for me? I might have to pull one out of my hat. All right, here's a really dandy little problem, the kind that I give when the class has been bothering me. 3.44. It's a beauty. I don't know if I assigned this one. This is the kind of problem that challenge you. Oh, doggone. Both of these things are taking, I wanted one where there was something left. I thought one of these switches to the other, went the other way. All right, that's the problem. And they actually want the voltage across that 4 ohm and the current through the 6. So really what they want is this. They want the voltage here, and they want the current here. That's what they're after. You don't want them, not yet. The only thing you want is the current through that inductor. Follow me? So here's my convention. I always go from top to bottom, left to right. This is my current, IL of T, as I've defined it. You all follow me there? This isn't going to be as tough as I wanted it. I could make it as tough, but for now we'll do this one. You have the solution for this. You all see this? Same, everything applies the same as before. First we find the current IL, T less than or equal to 0. I'm going to redraw the circuit. For T less than or equal to 0, what does that inductor look like, people? Short circuit, right? So it's going to become a short circuit. I'm going to redraw this.
Is that inductor 2 Henries?
2 Henries. It should be 2 Henries. I've given you, the printout. Can you see all the problems, class? How many's taken a look at that? You all, they should all be there. I gave you the entire chapter's problems, right? And I gave you all the solutions too. I did. Are you able to see the solutions?
No, yes, sir, it is, it's just that looks.
It just
sort of
looked like an
sister and not really.
Oh, yeah. That's a fair comment. I'm, anything but good at drawing anything. I'm just being honest with you. I try my best. That's meant to be an inductive. Now, what I wanted to get for T, less than or equal to 0, that's 12 volts. I don't have much time. Then I have a switch that's closed, and I have 4 ohms. Then I have another 4 ohms here. And then I have, this is a short, and here's my current, IL, that I'm after. And then I have 6 ohms here. And I have 3 ohms here. And then I have 6 volts. Now remember, well, I'll put it as a battery. Doesn't matter what it shows. That's plus to minus 6. Now, a lot of people freak out when they see this, oh, I don't have any idea how to do that. You don't need to do it, make it hard on yourself. I'm gonna do it probably the easiest way, in my opinion. I want the current going from here to here, right? Now, what I can do is do a source transform here. Please just watch this. Do you agree with that? Everybody? And can I do a source transform here as well? Agree? Source transform, right? Series resistor, series voltage source becomes parallel current source in parallel with that, right? So here's what's going to happen. And I'll draw that right here. What happens is now I'm going to have a current here. Just watch this. I'm going to have 12 by 4 is 3 amps, right? It's going to be in parallel with 4 here. Then I have another one, another 4 ohms, right? Then I have my little guy here that I've got to figure out the current through. And then I have 6 here. And then I have source transform here. 6 by 3 is 2 in parallel with 3. Y'all agree with me? Everybody? How many see this right here? Gotta make sure. Everybody? I just did a source transform, that's it. On both sides, right? Now, bear with me here. Y'all see these two are in parallel? How many do? 4 and 4 in parallel is 2 ohms. Now, isn't that 2 ohms and that 3 amps, and I've got a current in parallel with the resistor? I can multiply the 3 by 2 and get a voltage source, do you agree? And put it in series with 2, correct? And that's about what I'm gonna do. So this is gonna be 2 times 3 is 6 volts. In series with 2 ohms. Now remember, this is where we want the current, right here. Now that's 2 ohms. What am I going to do here? 3 in parallel with 6 is, yes?
Because you have I between the 2 amp sources, that's why you can't combine them, right? You can't combine the 2 amp and the 3 amp because they're in parallel.
Well, I'm trying to get this current. That's the problem. I've got to get that current, so I can't combine any. I have to put everything on one side here and one side here. Find the current going through there. Yes, sir?
Why not source transform with every resistor it's in parallel with? Why just do the first?
Well, remember, we're trying to find the current here, right? If we transform these two, we can't distinguish the current.
Can you do the 3 though? That last 3?
Well, we're going to do these two, right? What is it going to happen? This becomes 2 ohms, don't they? We're going to do that one. So these two become 2 ohms. Do you all agree with that? These two are parallel, aren't they? You see that? You're looking at me like a puzzle book.
There was something at a race that I missed when I was writing up there at that top right portion.
4 and 4 in parallel. That's
Yes,
2 ohms.
when it was a 4.
This two were in parallel. It's 2 ohms. Right?
Yes.
Source transform 4, and then you have 3 amps in parallel with it. Everybody's leaving. Sorry. All right, here that's 2 ohms, right? 2 and 2 is 4 volts, right? In series with 2 ohms. Do y'all agree with me here? So I got 2 ohms there times 2. So this becomes what? 2 ohms here. And this is going to be, class,
4 volts.
plus to minus 4 volts. Do y'all see this, class? With me? Now, pay attention to this. When I take a look and I want the net current flowing that way, just follow me. I get a volt, if I start here, voltage increase is 6, right? Minus 2 times I, minus 2 times I, or minus 4 times I, and then minus 4, right? So I have a net of 2 volts pushing current around, and it's going through 4 ohms. Do y'all agree with me? And that means that current, and I'm about out of time, as t less than or equal to 0, that current is going to be equal to 2 over 4, or it's 1/2 of an amp. Do y'all see that? You can do the math on this one later. Let me just finish this problem. Now, once these switches kick, open, right? For t greater than 0. That happens and that happens, correct? Is there a source that can power current through that inductor for t greater than 0? Class? No. What is the current going to go to? 0. All right, now you've got the second equation. Then you need R Thevenin, right? No, just last part. I mean, when we want the Thevenin equivalent resistance, we take out that, right? Yes, sir.
You guys tell me now.
I probably have a lot of this. I'm trying to get this thing done. Y'all follow me on this, class? Don't worry about that. Follow me on this. Now, what's the resistance? Thevenin equivalent resistance? Do we care about that resistor, class?
No.
Why not?
Because it's a short.
No current can flow there. Do we care about this resistance? We care about only these two, and they are in series, right?
Oh, yeah, they're-
Series. This is effectively gone. Look. This is gone. That's gone. That's gone. Only the 6 and
4.
what was that, a 3 or
4.
4? So it's 10 ohms. Agree? How many see this? Finish it up. I'm going to give you some more problems. You ready for the quiz?